Okay, so good evening, everybody. Can you hear me?
Yes, sir.
Okay. Okay, so in the last lecture, we have seen the K-map and we have minimized the expression by using the K-map. Okay. And also we have seen the half adder circuit and the full adder circuit. So today we are going to start with the comparator. Okay. We are going to design the comparator. So the comparator is what? A digital comparator is a combinational circuit that compares the two-digit binary numbers in order to find out whether one binary number is equal or less than or greater than the other binary number. Okay. So we logically design a circuit for which we will have two inputs, one for A and other for B, and we'll have the three outputs, that is A greater than B, A equal to B, and A less than B. Okay. So we are going to compare the two single bit numbers, that is A and B, and we are going to get the three outputs, that is A greater than B, A equal to B, and A less than B. This is the circuit for the n-bit comparator. So here you can see the block diagram for the comparator. We are having the two inputs A and B, and the output is A greater than B, A equal to B, and A less than B. So this is the one-bit comparator circuit. So the comparator is used to compare the two bits. It's called as a single bit comparator. So it consists of two inputs, each for the two single bit numbers, and three outputs to generate the less than, equal to, and greater than the binary, greater than between two binary numbers. Okay. So truth table for a one bit comparator is given below. So here we are having the two inputs A and B. So A can be 0, B can be 0. Okay. The first input is so two inputs, so we can have four combination, that is 2 raised to 2. Okay, 0, 0, 0, 1, 1, 0, and 1, 1. And we are having three outputs, A less than B, A equal to B, and A greater than B. So when A is 0 and B is 0, what is happening? The A equal to B output is high, and A less than B and A greater than B output is 0, 0. Okay. When A is 0 and B is 1, A is less than B. So A less than B output is 1, and A equal to B and A greater than B output is 0. For A is equal to 1 and B is equal to 0, the A greater than B output is 1, and A less than B and A equal to B output is 0. For A is equal to 1 and B is equal to 1, A is equal to B output is 1, and A less than B and A greater than B output is 0. Okay. So in this way we can see the truth table for the one bit comparator. So from the above truth table, the logical expression for each output can be expressed as, for A greater than B it is A dot B bar, for A less than B it is A bar dot B, and for A equal to B it is A bar dot B bar plus AB. Okay. So we can find out the expression by using the K-map. First we'll draw for the A less than B. Okay. So we are having the two variables, so we can draw the two variable K-map, that is two inputs A and B. Here we can have A is 0 and B is A can be 0 or 1, B can be 0 or 1. Okay. So when A is 0 and B is 0, for A less than B the output is 0. When A is 0 and B is 1, A is 0 and B is 1, the output is 1. A is 1 and B is 0, the output is 0. And A is 1 and B is 1, output is again 0. Okay. So we can encircle this one and we can write down the expression for this is A bar dot B. Okay. A bar dot B. Then for A greater than B, you can again draw the truth table. You can draw the K-map, sorry. Here are in the two inputs A and B. A can be either 0 or 1 and B is 0 and 1. Okay. So for A is 0, B is 0, output is 0. For A is 0, B is 1, output is 0. A is 1 and B is 0, output is 1. And both the inputs are 1, output is 0. So we can encircle this one. And the expression for this is A dot B bar. Because here A is 1 and B is 0. For 1 we can write down A and for 0 we can write down B bar. Now for A equal to B, what we can do? Again we have to draw the K-map for this. We are having two inputs A and B. A can be 0 or 1. Again B can be 0 or 1. So when A is 0 and B is 0, output is 1. When A is 0 and B is 1, output is 0. When A is 1 and B is 0, output is again 0. When A is 1 and B is 1, output is 1. Here we are having 1 and here we are having 1. So for A equal to B, the expression is what? That is A bar dot B bar plus A dot B. Okay. So this is equal to what? A X nor B. Okay. A X nor B. A X nor B. This was for the 1-bit comparator. Okay. Here we are in circuit diagram. Two inputs A and B. And for A greater than B, the output is what? A dot B bar. For A less than B, it is A bar dot B. And for A equal to B, it is A X nor B. Okay. You can see here the circuit diagram for the 1-bit comparator. Okay. Any doubt in this? Okay. So we'll go to the next topic, that is flip-flop. Okay. What is a flip-flop? Flip-flop is a single bit memory element. Okay. So it stores either 1 or 0, that is, it is not blank. So it is used in the sequential circuit. For example, it is used in the counters, shift register, digital clocks. Okay. So it is also a basic block of computer memory. Okay. Example, RAM and ROM. So it is also a basic block of computer memory. So different types of flip-flops we are having: the SR flip-flop, D flip-flop, JK flip-flop, and the T flip-flop. So SR stands for what? Set reset flip-flop. So SR stands for set reset, and D is the delay flip-flop, and JK stands for Jack Kibble, and T is the toggle. Okay, T is the toggle flip-flop. These are different types of flip-flops. Okay, SR flip-flop, JK flip-flop, T flip-flop, and the D flip-flop. Now we are having the triggering methods. So we are having two types, that is level triggered and the edge triggered. In the level triggered, we are having the positive level triggered and the negative level triggered. And the edge triggered, we are having the positive edge triggered, that is leading edge, and negative edge triggered, that is the trailing edge. Okay. What is the positive level triggered? So here we can see the symbol for the positive level triggered. This is the symbol for the positive level triggered. Okay. So this is the two input, this is the clock, and these are the outputs Q and Q bar. Positive level triggered means when the clock is 1, that time we get the change in the output. Okay. When the clock is 1, that time we get change in the output. Okay. And negative level triggered. So this is the negative level triggered symbol. Here we are having the clock and the bubble. So this denote that it is a negative level triggered. Okay. So negative level means when the clock is 0, that time we get change in the output. Okay. Here we are having the two inputs, and these are the outputs. This is for the negative level triggered flip-flop. Next is the edge triggered. In that we are having two types. That is positive edge triggered, that is known as leading edge. This is a symbol for the positive edge triggered. So here we are having an arrow and these two inputs and these two outputs. Positive edge triggered means when the clock changes from 0 to 1, that time we get change in the output. And negative edge triggered means this is the positive edge. Means when it is going from 0 to 1, that time we get change in the output. And negative edge triggered is the symbol is here, one arrow and the bubble that indicates that is negative edge triggered. Negative edge triggered, or it is known as the trailing edge. Okay. When the clock goes from 1 to 0. Okay, that time we get change in the output. It is known as negative edge of the trailing edge. Okay. This was about the flip-flop. Any doubt in this flip-flop? Next, we are going to the next type of flip-flop, that is the SR flip-flop. Okay. So the SR flip-flop is also known as the SR latch. Can be considered as one of the most basic sequential logic circuit. Okay. So the simple flip-flop is basically 1-bit memory bistable device that has the two inputs, one which will set the device, meaning the output is equal to 1, and it is labeled as S, and one which will reset the device, meaning the output is equal to 0, that is labeled as R. This SR flip-flop on the triggering edge of the clock pulse. Okay. When S is high and R is low, it is known as the set state. When R is high and S is low, it is known as the reset state. And when both the inputs are low, it is known as no change. And when both the inputs are high, it is known as the invalid state. Okay. These are different conditions for the SR flip-flop on the triggering edge of the clock pulse. This is the circuit diagram and the truth table of the SR flip-flop. So here we are having the two inputs S and R. S stands for set. S means what? Set. And R stands for reset. S stands for set and R stands for reset. Okay. So this is the SR flip-flop and the clock is given here. This is a circuit diagram for the SR flip-flop. Okay, so we are having the 4 NAND gates. S and R are the input and clock, and Q and Q bar are the outputs. Okay. So when the clock is 0 and S and R can be either 0 or 1, the output Q and Q bar are no change or same as the memory. Okay. No change or same as the memory. When the clock is 1, S is 0 and R is 0. Again, the output is no change or same as the memory. Okay. When the clock is 1, S is 0 and R is 1. Output Q is 0 and Q bar is 1. Okay. When the clock is 1, S is 1 and R is 0. Output Q is 1 and Q bar is 0. When the clock is 1, S is 1 and R is 1. Output Q is, both the output tend to be 1. That is known as the invalid condition or the forbidden condition. Okay. So we'll see what is happening when we'll give the input. Suppose S is 0 and R is 0 and clock is 1. Okay. And the output Q is 0 and Q bar is 1. So when S is 0 and clock is 1, so 0 and 1 output of this will be 1. And when clock is 1 and R is 0, output of this will NAND gate will be 1. Okay. So this one will go here 1 into 1, the output here will be 0. And this 0 will come here 0 into 1, the output here is 1. So whatever we have, whatever was stored before, that only we are getting at the output. That is known as the NC, means no change. No change condition. Okay. There is no change in the output. You see the next case when the clock is 1, S is 0 and R is 1. Okay. So again Q is 0 and Q bar is 1. So when S is 0 and clock is 1, 0 and 1 output here is 1. 1 into 1 output here is 0. Okay. If this one will go here 1 into 1 output here is 0. And this 0 will come here 0 into 0 output here is 1. So again in this case what is happening? Q is 0 and Q bar is 1. So this is known as the reset state. Flip-flop is reset to 0. Okay. This is known as the reset state. Okay. This is the next case now. When S is 1 and R is 0 and clock is 1. 1 into 1 output of this NAND gate is 0. 1 into 0 output of this NAND gate is 1. This was Q is 0 and Q bar is 1. So this one will go here 1 into 0. Output here is 1. And this one will come here 1 into 1. Output here is 0. So now the output is 1. Q is 1 and Q bar is 0. Okay. Q is 1 and Q bar is 0. That means that it is gone into the set state. Okay. Flip-flop is set to 1. This is known as the set state. Okay. This is known as set state. Yes or no? So now S is 1 and R is 1 and clock is 1. So 1 into 1 output here is 0. 1 into 1 output here is 0. Okay. So this Q was 1 and Q bar was 0. This 0 will come here. 0 into 0 output here is 1. This 1 will come here. 1 into 0 output here is 1. So both the outputs are tend to be 1. That is known as the invalid condition. Okay. This is known as the invalid or the forbidden condition. Okay. Invalid or the forbidden condition. Invalid or the forbidden condition. Here you can see the symbol and the waveforms for the SR flip-flop. S and R are the inputs, this is the clock, and Q and Q bar are the outputs. Okay. So during this clock cycle, first clock cycle, what is happening? Here S is 1 and R is 0. Okay. When S is 1, R is 0, flip-flop is set to 1. Next, S is 0 and R is 1. So flip-flop is reset to 0. S is 0 and R is 0. Okay. For 0, 0, the output is no change. Means whatever was stored before will get at the output. Okay. This is the working of the SR flip-flop. Any doubt in this SR flip-flop? Okay. Next we'll go to the next flip-flop, that is the JK flip-flop. So JK is basically a gated SR flip-flop with the addition of the clock input circuitry that prevents the illegal or the invalid output condition that occurred when both the inputs S and R are equal to logic level 1. Okay. So in the SR flip-flop, when both the inputs are 1, S and R are 1, the output of Q and Q bar tends to be, both the output tend to be 1 and that is known as the invalid condition. The most versatile of the flip-flop has two inputs J and K. The most JK flip-flop are based on the edge triggered principle. Okay. So they are triggered on the edge. So do not have any undefined state like the SR flip-flop. Okay. So when J and K both equals 1, the output toggles on the active clock edge. Okay. Here you can see a symbol, circuit diagram for the JK flip-flop, and this is the truth table. Okay. So here you can see that the output Q is given as input to this NAND gate, and the output of this Q bar is given as input to this NAND gate. Okay. Here we are having J and K are the inputs, this is the clock, and Q and Q bar are the outputs. Okay. Now again we'll see what is happening when the clock is 0 and J and K can be either 0 or 1. The output Q is what? No change or same as the memory. Okay. When clock will be 1, what is happening when the clock is 1? When clock is 1, So here we can see that when the clock is 1 and if J is 0 and K is 0, what is the output? So you can take that Q is 0 and Q bar is 1. So this one will go here and this 0 will come here, okay? 0 into 1 into 1. 1 into 0 into 1, the output here will be 1 and 1 into 0 into 0, output here also is 1. Okay? Suppose this 0 will come here, 0 into 1 here 1, this one will go here, 1 into 1 output is 0, okay? So again we are getting 0 and 1, means when J is 0 and K is 0, output is what? No change. Okay? When J is 0 and K is 0, output is no change. Output is what? No change. We'll see the next condition now. When J is 0 and K is 1 and clock is 1, what is happening? So now Q is 0 and Q bar is 1. So this 0 will come here and this one will go here. So 1 into 0 into 1, output here is 1. 1 into 1 into 0, here also output is 1. What will happen? This one will go here, 1 into 1, output here is 0. And this 0 will come here, 0 into 1, output here is 1. So here what's happening? Q is 0, we are getting Q is 0 and Q bar is 1. So this is known as the reset state. Okay? This is known as the reset state. And next is what? Clock is 1, J is 1 and K is 0. Okay. So this Q is 0 and Q bar is 1. So this one will come here and this 0 will come here. Okay. So 1 into 1 into 1, output here will be 0. 1 into 0 into 0, output here is 1. Okay. What will happen? This one will go here. So 1 into 0, output here is 1. This one will come here. 1 into 1, output here is 0. So Q is 1 and Q bar we are getting 0. So Q is 1, that is known as the set state. Flip flop is set to 1. Is known as the set state. And last is the toggle. Okay. So now we'll see the toggle state. When J is 1 and K is 1 and clock is 1, what is happening? This Q is 1 and Q bar is 0. Okay. So this one will come here. This 0 will go here. 0 into 1 into 1, output here is 1. 1 into 1 into 1, output here is 0. Okay. So this one will come here, 1 into 0, output here is 1. This one will go here, 1 into 1, output here is 0. Okay. So it is toggling from 1 to 0 and this is Q bar is 1. Okay. So this is known as the toggle condition. Okay. First it was 1, Q was 1, it is toggled into 0. Okay. This was working on JK flip flop. Here we can see the symbol. In the symbol, what we can see, there are two inputs J and K, and the clock. Clock is shown by the arrow. The arrow indicates it is positive as triggered. Okay. And the outputs are Q and Q bar. This is a symbol for the JK flip flop, J and K, clock, and two outputs Q and Q bar. Okay. So here you can see this is the clock. This is the clock. So during this, when J is 1 and K is 0, when J is 1 and K is 0, what is happening? The output Q is 1. Okay. Next clock cycle when J is 0 and k is 1, the output q is 0. When j is 0 and k is 1, output q is 0. Okay. When j is 1, k is 1, output is toggling from 0 to 1. When j is 1, k is 1, output is toggling from 1 to 0. Again, j is 1, k is 1, output is toggling from 0 to 1. Okay. So in this way, we are getting the output for JK flip-flop. Okay. Any doubts in this JK flip-flop? Anybody having doubt in JK flip-flop? Now I give one problem. So I'll give one expression. You have to minimize that is in the K map. Okay. So the expression is what f is equal to a bar b bar c bar d bar plus a bar c bar d plus a bar b bar c d bar plus a bar b bar c d plus a b bar c d plus a b c bar d bar plus a b c d bar plus a b c d. Yes, we have to solve this by using K map. Okay. Solve this expression and tell me minimize the expression. Okay. Simplify using K map and tell me the answer. Got the answer for this? For this, you have to draw the four variable K map, okay? Here we are having input 0, 0, 0, 1, 1, 1 and 1, 0. Here also we are having 0, 0, 0, 1, 1, 1 and 1, 0, okay? Here we'll write the values of this. A bar means 0, 0, 0, 0. This means 0, 0, 0, 1. This is 0, 0, 1, 0, 0, 0, 1, 1. This is 1, 0, 1, 1. This is 1, 1, 0, 0. This is 1, 1, 1, 0. This is 1, 1, 1, 1. Okay. So these values you have to put here. So for 0, 0, 0, 0, this is the SOP expression. Okay. So this is the SOP expression, sum of products. So wherever we'll see the product term, we have to write down 1. For 0, 0, 0, 0, here we can write down 1. For 0, 0, 0, 1, 0, 0, 0, 1, here we are writing 1. 0, 0, 1, 0, here we are writing 1. 0, 0, 1, 1, here we are writing 1. Okay. Next is 1, 0, 1, 1. 1, 0, 1, 1, here we are writing 1. 1, 1, 0, 0. Here we are writing 1. 1, 1, 1, 0. 1, 1, 1, 0. Here we'll write 1 and 1, 1, 1, 1. Here we'll write 1. Okay. Now to the grouping. So we can do the group of these 4 ones. Okay. And these 2 will be in the opposite grouping. And the group of these 2 ones. Okay. So now this group of 4 ones, we can write down the value. So for these 4 ones, the value of C and D is changing, but the value of AB is 0, 0. You can write down here it as A bar, B bar. Okay. Here for these 2 ones, the value of C and D is same. The value of A is 1, 1 and value of B is changing from 1 to 0. You can write down A, C, D. Okay. And for this opposite grouping, the value of AB is 1, 1 and the value of C is changing from 0 to 1, but the value of D is 0. You can write down AB, AB, D bar. Okay. The final expression is, minimized expression is what? A bar B, A bar B bar plus AB D bar plus ACD. Okay, so this is the minimized expression. Okay. Any doubt in this? Yes, no doubt.
No, sir.
Okay. So who is the CR? CR who is absent? Who is absent for this class? Okay. Okay, then that's all for today. Thank you. We'll meet in the next lecture. Okay.
Thank you, sir.